The third property or rule that we'll be talking about today is called the power rule, which says log base b of m raised to an exponent p can be rewritten as p times the log base b of m. Essentially, you take the power or the exponent and move it down to become the coefficient. This does seem a little weird where you move the exponent down to be a number multiplied by the front, and some students might ask, where did this come from? And when they ask the question, where did this come from, this is the example I give. It's not quite as clear as the other two examples, but if I have x to the 3 all raised to the 4th power, in the laws of exponents, we multiply 3 times 4 because I have 4 copies of x cubed. So x cubed times x cubed times x cubed times x cubed, which is 4 copies, and the shortcut we use is just 3 times 4, which gets us 12. A little harder to see here, but first I was given a power to a power. X cubed all raised to the 4th. So there's a base and an exponent here. And what we did is we changed this power to become a product. So because I changed the x cubed raised to the 4th to x to the 3 times 4, I changed the power to a product. Let's see what that does over here. We have log base b of m to the p, which was a power. P was a power. When I moved it down to the front, it became a product. So it changed a power to a product. I know that's a little bit harder for students to see that it kind of came from that, but the power rule is still valid, and you can rewrite going forwards or backwards. Log base b of m to the p is the same as p times log base b of m. Or a shortcut is, if you just think the exponent of the argument can move down into the front, that's just a short way of thinking about this power rule. So when I move the 4 down to the front, I get 4 log base 5 of x. That's all I can do on this particular problem. Let's look at the next one. Again, we're expanding, so we're trying to make this as long as possible. So I move the 5 down in front, and that gives me 5 times log of 4x. So I've used the power rule to get the exponent out of the argument. But inside this argument, it looks like I still have a product or a multiply. So not only am I going to use the power rule, but I also have to include the product rule, which says log invisible base 10 of 4 plus log invisible base 10 of x. Because it's a product, I can change it to a sum of 2 logs. Now, I used a bracket here, or a big parentheses, to remind you that the 5 is being multiplied not only to the log 4, but also to the log of 5. So when I multiply this out, I get 5 log 4 plus 5 log x. And that answer is as expanded as possible. Our third expand problem may not look like there can be anything done, but there is a power rule that we can apply here. A lot of people look at the square root and don't remember that it is also an exponent. We can rewrite the square root of x as x raised to the 1/2 power. Once it looks like this, I can move the exponent, 1/2, down into the coefficient to get 1/2 ln x. And that's my final answer. Is as expanded as possible. Now that we've used our power rule to expand, we're going to do the exact opposite. We're going to use the power rule to condense. And remember, when we condense, we're condensing to a single logarithm. And this single logarithm cannot have any coefficient other than 1. So we'll say the coefficient must be equal to 1. So the reason 2 log x isn't already condensed, it is only a single logarithm, but we need to move the 2. The way I'm going to move the 2 is to use the power rule, but a little bit backwards of how we used it in the expand rule. I'm going to take this coefficient 2, and I'm going to move it up into the exponent of the argument to leave me with log invisible base 10 of x squared. Similarly, when I condense 4 log base 5 of 2, I can take the 4 and move it up into the exponent so that this log, this single logarithm, doesn't have any coefficient in front other than 1, which leaves me with log base 5 of 2 to the 4. But I can simplify 2 to the 4 and get log base 5 of 2 times 2 times 2 times 2 is 16. And that is my final answer. We have a few more examples for condense. Notice we have several rules working together here. Usually I like to condense using the power rule first. So every coefficient is going to move up into the exponent. I'm going to move this 2 up into the exponent of 6 and move the 1/2 to the exponent of y, which leaves me with log base b of x to the 5th minus log base b of 6 squared, which is just 36, minus log base b of y to the 1/2. I'm going to go ahead and write that the square root of y. So on this problem, I have now used the power rule to get all of the coefficients into the exponent of the argument. At this point, someone in class often says, well, how come you didn't take the -2? Well, I could have possibly taken the -2, and if I did, then I would have to leave a plus sign here instead of a minus sign. It actually doesn't really matter. I prefer keeping the negative with the log so that I can use the quotient rule. You could use it the other way, move the -2 up into the exponent, but then you have to remember that the negative exponent needs to move down into the denominator. The answer will come out the same whether you move the 2 or just the -2. I find this to be a little bit more helpful, and students make less mistakes when they do it this way. So what I'm going to do now is just take a look at the first two. Because we have the first log subtract the second log, I'm using the quotient rule, which says log base b of x to the 5th over 36. But I still have minus log base b of the square root of y. When I subtract two logs, I can take the log of their quotient. So this is going to get really messy here. I'm getting x to the 5th over 36, all divided by the square root of y. That obviously can be simplified by flipping and multiplying by the reciprocal. So I have x to the 5th over 36 multiplied by 1 over the square root of y, which just means the square root of y ends up at the bottom. So my final answer is log base b of x to the 5th over 36 times the square root of y. Now a lot of students at this point are like, wow, is there an easier way of doing that? That was a lot of work, especially when you divide it by another division, and the answer is yes, there is a shortcut here that I'd like to show you. Looking at our first step, log base b of x to the 5th minus log base b of 36 minus log base b of the square root of y. If my coefficient is positive and I have a sum of either addition or subtraction, a fast way of doing this problem is if my coefficient is positive, then my argument ends up in the numerator. If my coefficient is negative, then my argument ends up in the denominator. And the last one, my coefficient is negative, or I'm subtracting, so my argument ends up in the denominator. Positive ends up in the top, negative ends up in the bottom because of the quotient rule. And that saves us a lot of steps, but I get the same answer. So I like to use the rule of thumb when you're adding or subtracting. The positive ones remain in the numerator and the negative just remain in the denominator, so I don't have to keep dividing a fraction into another fraction, and it saves me a little bit of hassle in the long run. Looking at our last problem here, I'm still trying to condense to a single logarithm with a coefficient of 1. So that means all my coefficients need to move up into the exponent. So we have ln of x plus 7 cubed minus ln of x. Notice where bases are the same, so we can proceed. Because this is a minus, I know I have a quotient rule, which means I have x plus 7 cubed in the numerator because he's positive. In the denominator, I have x. This is my final answer. Please note that there's a common student mistake where when they look at a quotient rule, they'll say ln of this argument minus the ln of the other argument. And what they'll do is oh, I know that's a divide, and they'll take ln of x plus 7 cubed over ln x. This is not correct. The reason it's not correct is because they put an ln in the numerator and an ln in the denominator. All they've done is change the subtract sign into a division sign. But that's not what the quotient rule says. The quotient rule says if you take a log of an argument minus a log of another argument, you get a single logarithm, but you take the quotient of the arguments, not the quotient of the log of the arguments. You take the quotient of the arguments, and that has a single logarithm, in this case natural logarithm. So please don't make that common student mistake.